Thank you for all for coming to this lecture, and I really appreciate the opportunity that Amy offers to communicate my research to the OIST community. Basically, I was trained as a physicist in my undergraduate and my PhD, but when I came to OIST, I started developing this interdisciplinary research, and I can show you here how that changed my science throughout. Before I start, I would like to thank my collaborators. Good science is always done by wonderful people, and I was fortunate to have these collaborators through the years. Of course, most important leading guy is my PhD student, Margarita Dronova. She worked in my lab and made all this research possible. And we also have a collaboration with theorists and experimentalists across the globe on 3 different continents. For that, I always feel appreciated. Since my lab is doing research in magnetism, I feel it's important to go back a little bit to history to review our how magnetism relates to our civilization. So here is a Wikipedia page I grabbed to show our early understanding of magnetism, which is an impressive picture of the lodestone attracting iron nails. It's not a coincidence that we discovered this material after Iron Age, and both in Europe and in Asia. This is a very impressive demonstration of magnetism, but however, for about 2,000 years, this is the only thing we know about magnetism. We only know ferromagnetism. We don't know anything else. So now, coming into the 20th century, we have a little bit better opportunity to understand other types of magnetism. Now we know the atomic structure, and now we know the spins are individual ones attached to the irons. You can think about the spin as a small magnetic bar in the north and south sense. If you put them together, and they will align together, form the ferromagnetism, and this is explained by the Soviet physicist Landau. Using his mean field theory, he explained how a bunch of spins can form a ferromagnet through the phase transition. That works very well, and then there are other suggestions. Neil came in and said, okay, I might propose a different arrangement. I'll have spins going up, and the neighbor spin will go down, and so that they will alternatively arrange it. Of course, this arrangement was largely unknown because there's no magnetization attached to this. So because the spin, they cancel each other, so you actually know macroscopic magnetization. So you will not attract the iron nail with it. So that was his proposal. However, Landau said, no, it's not possible. Landau basically said it's not a quantum state. So it turned out that if you have 2 spins, if they want to arrange, they should have another state, which is a 1 down, 1 up, and these 2 should have the same probability. And they should have a superposition of the 2 quantum states to form a suitable quantum mechanical state. So in that case, this arrangement cannot be static, it has to be dynamic, keep on changing. In that way, you will not have this in a real crystal. Of course, ferromagnet is easier because you have them, the paired state is actually your paired state. So that was the difficulty, challenge at that time, until the experiment came out. So basically by 1951, the experimenters in the US, they built these neutron reactors and do the neutron magnetic diffraction. And they saw at the low temperature diffraction peak of the magnetism shows up. So basically, nil is justified. And of course, now we understand that the main problem is whether this is a quantum state or not is actually both ferromagnets and antiferromagnets are not quantum state. They are actually a direct product of the individual spin state on each side. So these spins are unentangled. So basically, they are much fixed in the space and forever. So here goes our understanding of long-range magnetic order. Basically, it's sort of like a classical picture in a sense. After that, basically, theorists start to think what other forms of spin arrangement you can have. Basically, this is a generation in the 1970s after the first generation of Landau and Neal. So Phil Anderson is a big player in that field, and although he got a Nobel Prize for his Anderson localization of charge transport in the disorder materials, he has a very big footprint in the magnetism field. In the early days, he proposed this spin ice picture through this Pauling's ice rule, and it's a trapped entropy part. Then later on, he actually proposed this RVB state, which is actually made of this exactly quantum state we talked previously, with two spins on the side, and they're superposition to each other. And then this configuration actually is allowed to change over time. And then this single site will become a spinel excitations by themselves. However, this state so far hasn't been proved yet, and so still is conjecture. On the other side, in 1975, with experimental evidence, Anderson and Sam Edwards of the UK, Cambridge, I think, they developed this replica model to describe spin glass experiment phenomenon. Basically, the model is composed of a multiple minimum in the parameter space, so that the system can sit in any one of the minimum positions and form the ground state, sort of. This turned out that this replica model is very difficult to handle in a theory, and only was resolved later by Parisi and using very creative mathematical tools. So Parisi got a Nobel Prize in 2021 based on this mathematical creations. However, the Nobel Prize did not give specific say this is given for the spin glass state. The mathematical tool turned out to be very, very useful and lead to Hopfield to develop his Hopfield neural network very quickly in 1979, I think. When this, and Phil Anderson actually observed that back in the 1990s and commented on that connection between their works. Now, this is all good for the mathematical part. Now, this mathematical trend keep on going. So the key point here is we are really searching for a spin liquid phase based on this Anderson's RVB kind of perception. It turned out that the work was done actually a long time ago by Hans Bessie. Hans Bessie actually, he got a Nobel Prize for something else, astrophysics, I think. But he has a Bessie ansatz in the 1931, and which actually was not quite understood for over a half century. Basically, this Bessie ansatz is dealing with a one spin chain of spin 1/2 spins. So you can see here is the spins aligned in antiferromagnetic neighbor to each other, forming a one-dimensional chain here. You can notice that you can pick any neighbors to form a spin singlet state, and you can also view this as a spin singlet ensemble in a one-dimensional space. Now you do a very small trick, is flip one spin. You say, okay, I want to flip one spin, and we want to create some inconvenience for you. So basically you can see for this red spin, which is flipped from this previous position, and the change in the spin moment is, angular momentum is h bar, which is a quantum number. It makes the two neighbors very unhappy. The two neighbors are aligned with this red spin in a very awkward position, ferromagnetic condition, instead of antiferromagnetic condition, which naturally should be. So then what happens, right? So you ask, what can we do about that? The spins don't feel happy. So what they did is actually, for this singlet, you can see they will flip. They will go to the other state. And they will, the left neighbor also does the same, and they go to the different composition. In that way, you actually make this original red spin position happy. So now that this spin has two basically antiferromagnetic neighbors. And the awkwardness, of course, is shifted in space. And the awkwardness is shifted on both left and right. So that now you have two red spins here and have a neighbor of a ferromagnetic spin. And in that way, you actually split this awkward situation in two. So what in the mathematics of quantum mechanics, you don't call it awkwardness. You call this excitation of angular momentum of h bar. So you split this angular momentum into two angular momentums, each one half h bar. That allows you to create the fractional excitations. You basically have the 1/2 of excitation on two of them together to give you original flip. So this is the first feature of the quantum spin liquid. Basically, is that you have fractional excitations. Now, there is a second feature of a quantum spin liquid, which is actually called topology. So basically, Haldane basically later realized that if you take the one-dimensional spin chain and you put it in a put it in a time scale, put a second axis on this with a time as the axis. So you are basically stacking different time evolutions in the two-dimensional space. Now here you can see, and for a pair of spins, here, for example, it wants to get to here by flipping 180 degrees. They have a choice. They can flip clockwise like this to flip over to here. They can also flip counterclockwise to here. So now imagine half the chain at the dividing line, the dashed line here, decide to flip counterclockwise on one side and decide to flip clockwise on the other side, right? So they don't know each other. They only know their neighbor block. So they decide happen to the one block middle of this, they rotate it counterclockwise differently. I mean, so basically at this point, you happen to know you have a very concentrated ferromagnetic state. And this concentrated ferromagnetic state is very different from everywhere else you have an antiferromagnetic state. So this turned out to be a topological defect, or rather topological charge. And this mapping of the one-dimensional space and the time in a quantum mechanical sense can be mapped onto the two-dimensional real space, which was studied by David Solis a couple years ago, and then so-called Costellis-Solis transition. And this is not a phase transition, but it's a topological state at a certain temperature. And you can have different topological charge with +1 and -1 types. So these are our fundamental understanding of the quantum spin liquid in both the topological state and the fractional state. And of course, the modern days, we have better, more complete, this generation will have more complete theoretical work. Basically, Xiaogang Wen and Alexei Kitaev has developed the complete mathematically rigorous theory framework for this quantum spin liquids. And back into the in 2008, Patrick Lee was hailing that we have the end of the drought of the quantum spin liquid. That year, we discovered a two-dimensional material called Herbert-Smith, which has a Kagome lattice. So you can see this gray triangles forming a two-dimensional triangles arrangement. And at that time, it was a very big breakthrough, and Patrick was certainly very happy about it. However, it's not quite exactly yet, and so we keep on working on this, and so we actually, over the next 25 years, we still are searching for the quantum spin liquid material and the real world examples. And of course, I mean, there are some focus on Kitaev state and some, but all 5 of these are the experiment surveys about possible materials. So far, 20 years later, the drought still continues. So what happened? So there are basically 2 things happened. I called it a nail and a hammer problem. So let me explain this. So at the beginning, it's a nail problem. So which sample system you want to work with to have the quantum spin liquid system. What Patrick hailed about is a system called Herbert-Smith, and we can use that as an example. Basically, in 2008, this material was discovered, at least the crystal structure was understood. Then in 2011, an MIT group has grown very good crystals, very large ones, 5, 6, 10 millimeter size. My student will be really envious about. Sorry. The crystal lattice, as we show here, is made of the copper in a so-called Kagome lattice. Is this Japanese weaving basket shape of this this form, and essentially the supposedly support frustrated spin interactions. However, and also that the Yang Li's group at the MIT quickly did a neutron scattering. Basically, they show this green region, which is a continuum, is what expected for the quantum spin liquid, because you're supposed to excite a pair of excitations which lead to the continuum excitation over this space. So that was actually the very rosy picture at that time. However, it's only understood later in 2016, Michael Norman wrote a review article criticizing this situation, basically saying that the crystal itself have 15% of copper sitting on the zinc side. So this material has significant amount of disorder in the atomic side. And then later on, the European group did more work on this and realized that it's more complicated. On both zinc side and copper side, you can have the mixture. You can have a significant amount, about 8% mixture on the copper side, and in the zinc side, you could only fill up to about 93%. And you cannot do better than that. So basically, the lesson 1 is nominally store each of matrix crystals, you could have uncharacterized disorder. And it is up to the sample grower and the material developer to ensure that the sample is as clean as they claim to be. Okay, so the second problem, second issue with this experiment situation is we don't have a hammer. The hammer basically is that you need to have an experiment technique or probe which can directly probe the quantum state, or rather the topological unique state. And unfortunately, our physical probes mostly do not have this kind of capability. So here is one example by Itamar Kinchi and Patrick Lee. They wrote a critique, I would say, rather a thought experiment. So they developed a theoretical model of disordered spin singlet. They don't need to have any quantum coherence. And they model that system for the heat capacity you typically measure. You measure that heat, then you compare with experimental measured heat capacity in the field for 4 different spin liquid candidates. You realize they all scale in this kind of this bumped shape, like this bumped shape, like his theory would predict. Right. So this is a very simple shape, and they can model a different type of physics, and then your experiment data actually can match with that. Basically, that says your physical measured quantities might have different interpretations once you're dealing with quantum spin liquid candidates. So you cannot preferably interpret your data towards the most favorable scenario for your taste. But you need to really evaluate the situation with all kinds of different possibilities. I mean, of course, unless you have very specific tools which can directly address this topological state. Now, let's take a page about what the other successful case will do. So actually, there's a very successful story about a fractional quantum Hall state, which basically in the 1983, when it was close to when first discovery, some of the quantum states are not very clear, like this 5/3 and the 4/3 state marked by these red arrows. However, with years goes on, by 2021, this quantum state of 5/3 and the 4/3 are a fully developed quantum state with 0 resistance here. This takes about 40 years development to get a cleaner crystals. And especially from 2007, 2020, they made about 2.5 times improvement in the mobility. So you think about that, 13 years of life, you actually only improve a factor 2.5. So that is a tremendous amount of effort at the Princeton. This group has been working on this for almost 40 years. They were involved in the original work as well too. So in this system, actually, we see the very good example of the 2 problems I named here, the hammer and the nail. So the hammer, they have the edge current, which can couple to the fractional quantum Hall state with a normal electrical circuitry. And the nail is a quantum state, they are actually more prominent with less chemical disorder. And these people took the hard way to purify it over 40 years. We actually have, for the spin system, so that's for the charge system. This is for the spin system, we have certain understanding about this behavior. We know that there are spin frustration and this chemical disorder. Spin frustration is actually a very simple concept to understand. You can think about this triangular lattice with 3 spins on the corner of it, and you could only have it up and down choices. And they have to interact with antiferromagnetism, means that the neighbor's spins would prefer to align opposite direction. Now you can see for the top one, if it's pointing up, this one pointing down, then this spin becomes very awkward. It doesn't know whether it's pointing up or pointing down. So this is called a spin frustration. And this is actually purely based on the geometry of the system. Of course, chemical disorder is another thing which is actually dependent on the sample quality, right? So we actually have a list of ingredients which can lead to a quantum spin liquid, and you can have either insulator or metal, spatial dimensionality, geometry. This turned out to be the most important thing, as you have to have the geometry which potentially can support spin frustration. So the forms we know of are in the 2-dimensional space. So we talk about 1-dimensional story already. In the 2-dimensional space, we have the triangular, Kagome and Kitaev lattices. And the 3-dimensional space, we have this called pyrochlore lattice, which will be my focus point. The reason I pick pyrochlore lattice is mainly because this 3-dimensional materials are much more easy to handle during the preparation and measurement. And you can get to much higher quality with that. Of course, there's Anderson already designed the spin ice on this set of lattices. And then you also can have a classical spin liquid by having the antiferromagnetic nearest neighbor interaction of the Heisenberg spins. Turned out that this is actually a relatively trivial case because if you look at the s equal to 1/2 spin ice, basically you have this spins all point to the middle or point away from the middle of the tetrahedron. If you have 6 spins aligned like this in a head-to-tail ring like this, imagine at one moment you suddenly flip all of them to the opposite direction. Right? Then you still have, at the local side, you still have one in, one out, just opposite the one. Overall, this energy of this system should not change. So basically, this is a zero energy mode, which you allow to flip the whole 6 spins all together instantaneously. This actually is called a ring mode in this quantum spin ice, quantum spin liquid, classical spin liquid. And this actually, there's no gap, no energy separation between that. So it's a topological trivial case. But nevertheless, you can understand this very simply by these models. So our choice at this moment is about the spinel magnet zinc Fe204. This Fe204, so Fe moment sits on the B side of the material, which is a pyrochlore lattice. And the antiferromagnetism was studied very quickly after neutron diffraction became a powerful tool in the field. So 1956 already have published data on that. However, you can see, compared with the lattice, which is very sharp, the magnetic signal is very broad and diffusive. This actually is puzzling. And turned out Phil Anderson actually did spend time on this. And during his, in his paper of spin ice, he talked about this system to think about whether it will be a long-range order or short-range order. And he actually expressed the puzzle and then said, this is probably short-range order, and it's actually have ferromagnetic nearest neighbor interaction. So what does he mean by that? What he means actually is that if you have, if you measure magnetic susceptibility of the system and plot the inverse of magnetic susceptibility against the temperature, you actually can fit the data with so-called Curie-Weiss plot with a straight line here. And the intercept here tells you whether this is a ferromagnetic system or antiferromagnetic system. The positive value is a ferromagnetic system. However, if you look at the susceptibility itself, it actually is typically an antiferromagnetic system. So the puzzle really is for Anderson and for everyone else is that how do you have a ferromagnetic interaction dominated system have an antiferromagnetic phase? But of course, the data has been consistent through the years. And so that's the main puzzling. And the fact is actually the amount of this Curie-Weiss temperature at 100 Kelvin compared with the peak temperature of 13, the ratio between them is about 8. This is a very large number and typically regarded as a very strongly frustrated spin system. So in the past 20 years, you can see people always call this system a spin frustrated material and the geometric frustrated system. And all of them, most of them are using a single crystal as their samples. So that actually is the initial motivation for us to work on this system. We try to understand what is spin frustration, how do you have a ferromagnetic component and the antiferromagnetic transitions. Of course, the literature has lots of information already, and you can read it through it. And the material has been studied by neutron magnetic diffuse scattering in the past. So at 15 Kelvin, you have diffusive patterns, which is basically unchanging down to 1.5 kelvins. So basically, the system has not been changing throughout this temperature region, and it's very diffusive. And then this data is actually shows no long-range order at all, as we know from the 1950s. So we have consistency over 17 years. But you ask the question, is this really the intrinsic behavior? So we came to our conclusion that we need to grow our crystal ourselves. So basically, that's the best part of OIST is actually I can start the lab with material development instead of doing measurement I was used to do. At that time, I had lots of consultation with my colleagues across the world, especially issue 1 at the Oak Ridge. And basically, what I learned was for the they actually developed a technique to use a flux to improve the sample homogeneity and the quality. So I said, okay, I want to use flux too, but I want to use even lower temperature. So what we had started with is a so-called solution growth process. You use a platinum cup and put your components in that with a molten, a very low melting point oxides, which is a boron oxide, part of boron oxide family. Then you basically heat up to 1,000 Celsius-ish, and then you cool down slowly. You can see crystal develop on the wall here on the platinum crucible. And if you track it cleanly, you can get a very beautiful look crystal and with very flat facets. What we did differently is actually, because of this solution environment, we can actually control what we put in there. Instead like a floating zone growth, basically you have to have the precise composition because you cannot have a solution there easily. So what we have is we put into this solution a different amount of zinc and iron oxide, and then we measure the product in the crystal, how much iron and the zinc compositions are there. So you can see, not surprisingly, they have a correlation because the more zinc you put in there, of course, the more zinc you have in the final crystal. But nevertheless, you follow a monotonic behavior with the things you put in there. So you have control. The second, we actually have this different growth temperature from high to low temperatures. And you can see when you go to high temperature, you need to put lots of zinc to make it stoichiometric. But that actually creates lots of inversion disorder for the purpose of this crystal. However, if you grow at a low temperature, then you can put less zinc, much more close to the stoichiometric condition. And you have a much more stoichiometric material and also low level of the inversion disorder. So with 2 control parameters of the molar ratio and temperature, we can fight against the stoichiometry and inversion disorder simultaneously. We eventually understood how to characterize this crystal, and we actually, by using the AC magnetic susceptibility measurement. I'm not going to bother you with this measurement itself detail, but I can tell you is this chi double prime, which is dissipation component, compared with this chi prime, which is the response. If you can maximize it, it actually would be less disorder. So basically, you compare with the literature data, they have typically the chi prime over chi at a 3% ratio. In our best case, we have this chi prime ratio compared with the peak is only 0.1%. So you can see here by control your different growth conditions, you can have disorder about varying about 30 times in difference. And in our case, we can actually using other technique calibrate this to about 0.25% disorder to 5% disorder. And for the top 2, you typically have inversion disorder, and the lower one is mostly dominated by the stoichiometry. We bring our crystal to the neutron beamline. You can see here we actually have a single crystal behavior and with the magnetism and the lattice indistinguishable to each other. And this intensity is a plot on the log scale, so you actually have very low diffuse scattering here. And this is only our second best sample. By studying the line width of this material, we can verify this long range order as long range as our crystal itself. So basically, it's saying that we actually clean up the crystal. We prove that instead of all the spin frustration people talk about in this material, this system actually is a long-range antiferromagnetism. Now you ask, what's the discrepancy before with a ferromagnetic type of Curie Weiss temperature? It turned out that it's no longer there. Because if you measure our crystals, we have Curie Weiss temperature in the negative temperature with minus 25 Kelvin. So you compare with the peak temperature of 10 Kelvin, the frustration ratio is only 2.5. So this actually is not even strongly frustrated system. It's a mildly frustrated at the most. So we no longer have any discrepancy. All the previous data results in the past 70 years are due to the fact that you have uncontrolled sample disorder in the systems. So the take-home message, forget about physics. I'm a material scientist. So that's a part I appreciated a lot in my first couple years here when Margarita published her first paper. Now, it's time to take a break and think about it, what that means. Right, so we cleaned up this crystal, which has been bothering people for 70 years. But by and large, the physics is 1960s, Landau, Neal type of physics. You really, we haven't created anything new yet, per se. So you sort of took a little bit inspiration from this 1960 cartoon. The nation that controls magnetism will control the universe. I'm not that ambitious. I don't want to control the universe, not through the magnetism anyway. I don't think it works. However, the key question we can ask is, what can you do with the control of disorder in magnetism? Is that going to lead you to something useful, insightful in the research? Now we realize that there's still unsolved problem in the previous case, is that the system is a spin glass. It's said to be a spin glass, and you can see very clearly frequency dependence on this susceptibility, even for the stoichiometry materials. The spin glass phase is actually, as we mentioned before, was not resolved in the mathematical work. The mathematical work has its own rigorousness in the construction, and so that's why it's recognized. But however, there's not a experimental connection to the real materials. And actually, in experiments, we haven't really established what is the spin glass system. I mean, there's a lot of signature here and there everywhere. But actually, lots of people will say it's just a short-range spin clusters. So we really want to ask two questions. So what is the experimental identity of spin glass? How do we establish that? And then is this spin glass a thermodynamic phase to start with? Because in Parisi's theory, it has to be a thermodynamic phase because it's a phase transition theory. But of course, experiment, how do you prove that? So for that, we started another new set of crystals. Should thank Margarita for that, really a lot of work. But what the plan basically is you try to study the spin glass at its weakest moment, at its incipient stage. So once it starts to emerge, you start to ask what it looks like. So basically, we take a system, replace the zinc iron oxide, the iron with the gallium, which are both same chemical properties. We start to put gallium into iron position. Then you ask, what would happen? So this actually is a very challenging experiment, and you realize that at the beginning, we don't know how much disorder, too much disorder. So you have to be very, very careful for each composition. Eventually, you need to put lots of effort to minimize the amount of disorder. So basically, for each values here, shown here, we need to do a very careful study of this, growth parameter check. So it took us more than 100 growths to get this. However, it's actually very interesting because you measure the heat capacity, which is the red curve here, and measure the blue curve, which is a magnetic stability. You can see in the pure sample, they almost match, but a small difference. But once you start doping, they have large differences. And then you put the peak temperature onto this diagram with temperature versus doping ratio. You can see the blue curve has a monotonic behavior like this, but red curve has oscillation behavior. It's a non-monotonic, and also it oscillates around this blue curve. So once the doping starts, these two characterizations never appear to be consistent. And the worst part is actually non-monotonic. So you keep on wondering, what is the reason this has a non-monotonic behavior? However, you look at this position of this valley here, you realize it's important to have a very good control of disorder, because a couple more % of disorder, you might wipe out this whole feature together. So that actually speaks to the importance of disorder control that allows us to observe that this oscillation behavior at a very low disorder concentration. So with that, we take the three, so basically we take the three samples, one here at the purest condition, one at 97%, one at 86%. We take the three cases of the extreme position to the neutron experiment. And what you can see is actually this, at the high temperature, 10 Kelvin, for example, the behavior all the same. All three samples have exactly the same behavior. Diffusive, no peak, no bragg peak, and very consistent patterns across three samples. However, if you cool down to half the temperature, 5 Kelvin, what you see is for the disorder sample, it still remains more or less the same. The pattern does not change across the different temperatures. However, in the pure sample, you can see this very diffusive part becomes single spot. And the 97% sort of sitting in between, but you have very clear spot here. All right. So now let's take a break and let's think about what is the meaning of this measurement. So the meaning of this measurement is a neutron scattering of the magnetic ensembles, right? Magnetic correlation. So your sample is a magnetic material, have a spin correlation in the surface and at the bulk. Then you basically have neutron with wavelength lambda coming in, and this neutron does have a coherence length. And the scattering is only meaningful once this neutron flies over its coherence length L. So it has a coherence L and it has a speed. And for neutron to fly over its coherence length distance, and then you have the time scale lambda. So that's the observation time of a neutron to the spin ensemble. So if your sample is fluctuating too fast, shorter than the time constant here, the neutron sees the average. It will not register any signal. If your sample is static over this time scale, then you would observe spin correlations. And this is actually very easy to calculate. And the alternative way to calculate it is actually use energy uncertainty of your neutrons, and which is specified by the beamline itself. So we know that this values very well from the construction view. So with that, you actually can see for the specific neutron beamline we used, you get time constant of 1 picosecond, 10 to the minus 12 second. So that actually gives you a perspective about spin correlation in our disorder-fasted materials at this time scale. So now we actually look at our data slightly differently. What we do here is we take the difference between two neighboring temperatures and see how the spectral weight evolves from temperature to temperature to temperature. So what we have here is if at the high temperature from 10 to 15 Kelvin, you can see the red is accumulation. So basically all three systems have a spin density, a spin spectral weight accumulating at everywhere in the reciprocal space. You don't see any blue here. This accidental fluctuations, of course. But the spin spectral weight is positive across all three samples. However, if you go down to lower temperature, you can see For the stoichiometric sample, we actually have redistribution of the spectral weight from this interstitial region to the Bragg peak. And this continues for all the low temperature, subsequent low temperatures. For the disorder sample, however, this red accumulation of the spectral weight continues to the lowest temperature we have. So basically, there are two different type of behaviors. First one is the, you can see spin fluctuations and the redistribution in the sample. And the second one, you just see a static correlation accumulating on this time scale of 1 picosecond. Now we actually can do a much better job by quantitatively do an integration. So we actually, here's a scheme about how to integrate the reciprocal space, A, B, C, D, different schemes. We look at A scheme first, which is a large volume integration covering almost all the spin intensities. You can see for all three samples, if you normalize by the mass and mole of the iron, they are identical to each other. So that actually is, to me, this actually is one of the most surprising part, because you realize for disorder, with the presence of disorder, at 1 picosecond, spins don't see them. Spins actually, the dynamic of spins is only controlled by the temperature, but not by the disorder itself. The time constant at least is not changed. So you don't have any actual accumulation for the slowdown for the disorder sample. However, the distribution of in the reciprocal space does change. So if you see here, and up to 10 Kelvin, if you change the integration volume to have very small volume at the Bragg peak, or have very medium volume around this interstitial region, up to 10 Kelvin, the accumulation is still the same. So that confirms our previous picture that we cannot tell the difference between the spin fluctuations across three samples up to 10 Kelvin. However, after 10 Kelvin, you can see the Bragg peak and the clean sample, when x equal to 1, you have Bragg peak rising rather quickly. However, in the interstitial part, you have this spectral weight reducing to the lower values. However, the thing interesting is for the disorder sample, you don't have any redistributions, both on the 1.50 and 0.750, the spectral weight increases. Right. So this is actually the huge difference between your clean limit sample and the spin glass related sample. So now we actually can also study the correlation lengths. The correlation lengths of these orders at the magnetic peak, you can see, compared with the lattice correlation lengths, my x equal to 1 sample quickly saturated and it becomes same as the lattice correlation. However, the 0.97 sample has a long range correlation, but this value of the correlation length is slightly lower than what you have at the lattice. However, for the disorder sample, you actually never develop long range. It's always small. It's only basically 30% increase compared with the 15 Kelvin. At off spectral position, what you have is actually this, for the clean sample, you actually have a reduction of the correlation length. So basically that confirms the redistribution of the spin spectral weight to other positions. However, for the spin glass sample, you actually have keep on increasing of the correlation length. Means that your short range order in this system actually grows a little bit. So basically both at your magnetic position and also your off magnetic position, your short range order grows a little bit in both ways, both cases. So now actually we can start to understand this phase diagram of this system. What we have in the heat capacity evolution is that at the very close to the x equals 1 position, we have long range order. When you have more disorder, the long-range order become much more fragile. It takes lower temperature to stabilize. So the order in temperature become lower and lower because this disorder makes the growth of long-range order more difficult. However, it still dominates. It still dominates over your short-range order. Only until you have more disorder, then short-range order wins over. So this non-monotonic behavior is a competition between two organization mechanisms. One is single instability, one is multiple instability. And because they are crossing each other, you have this valley in your heat capacity. Of course, this doesn't say anything about spin glass. Now you really start become curious. What is a spin glass story? Spin glass story is actually turned out to be very quick once you understand this. Is that if you look at the 850C growth, there's no frequency dependence in my magnetic dissipations, or at least not observable ones, very small. In the pure sample, you start seeing a spin glass phase, frequency shifting between different measurements. And at the 97% sample, you can see clear shifting of this spin glass behavior. However, we already know that from our neutron diffraction that this is a long-range order sample. So basically, it is actually the spin glass phase is not only associated with short-range order, it also can associate with a system with a clear long-range order as well too. And beyond that is actually, in this 97% sample, you actually have this spin glass freezing temperature happening about 1.2 Kelvin above the long-range order develops. So basically, whatever the spin frozen here has nothing to do with long-range order developing here. So with that, you can actually conclude spin glass is not related to spin cluster at all. It's only the individual uncorrelated spins in the sample because you dope the disorder into it. I mean, it's sort of the anticlimax, but actually, you have to have experiment narrative to prove that. And that's our proof. Now we actually come to the conclusion of my talk. Basically, you can understand this phase diagram very well now. There's a spin glass phase, and there's independently the long-range order and the short-range order happening in this system. And they are rather uncorrelated, but they are actually characterized by different measurement techniques. Now, if you come to this roadmap to our search of the spin liquid, then you understand if in the system you have very little fluctuation, you are mostly along this direction. You have long-range order and the long-range order and spin glass, and short-range order and the spin glass. Now, if you want to get a spin liquid phase, you need to stay very, very close to the disorder-free limit. And we know now, actually, this number should be about less than 1% doping, and probably preferably 0.5% or less doping. That actually put a lot of stress in experiment cases that we actually need to grow crystals in extremely clean conditions in order to allow us to see the spin liquid phase. So that concludes my talk. Thank you.